Let me start by thanking the organizers again, especially Alessio and Enrico, who are here connected, and for the opportunity to speak about this recent paper I had in collaboration with my supervisor, Sasha Grozdanov. I promise the talk will be less boring than the title, and it's something that I'm really excited about, and I hope that I'm gonna manage to convey some of this excitement to you by the end of the talk. So to start, just let me give you an idea of how the talk is going to look like. So at the very beginning, I want to try to explain precisely what is the problem that we addressed in this paper together with Sasha. And in the next part, I will want to give a brief review of the closed time path formalism for quantum field theory, both because I do not expect all of you to be super familiar with it, but also because we're going to need some fine print details of it to actually address the problem. The bulk of the talk will be the third section, which is how to derive these dissipative EFTs that I mentioned in the title, and I will mention again in the beginning. If time allows, I'm going to be talking about these flashy structures that we found in these theories. There, some that look like RG fixed points, but maybe they're not exactly RG fixed points. I'm going to talk about it later, and I'll then conclude and give you a brief outline of what the future holds for this thing. So let's really start. Okay, so the standpoint I want to take is if you're like me, you're interested in transport properties of a condensed matter system, especially in late time, long distance transport properties. These are encoded in general, in infrared limits of thermal correlators of some conserved quantity. And so in line of principle, given any microscopic theory, you can calculate them, but it turns out that in general, it's disgustingly difficult. And what makes this even more difficult sometimes is that it may be very, very hard to know what the correct infrared degrees of freedom of a theory actually are, because in the RG flow that connects you to the fundamental theory, to what actually describes the long distance physics, anything can happen. There can be confinement, there can be emergent degrees of freedom that are collective. So this is very, very difficult. And this is why, you can adopt a different standpoint, which is the effective field theory standpoint, in which, using some stronger mathematical and physical reasoning, you can actually guess what a theory at, in the low energy limit it does look like. And in particularly, I'm referring to this approach advocated by Crossley collaborators starting from 2015 and in a series of subsequent papers in which they worked with these theories defined on a Schwinger-Keldysh contour. I'm going to explain what this is later, which has been quite successful in tackling a lot of old and new problems in thermal physics. So the reason of the success is that this is like a very consistent, this is a very stringent framework in which you can have a systematic derivation of these effective actions, and really, and it can be applied to many different things. So people like this. Now, let's review this. So to briefly understand how this works, so the idea is that what you will be interested in is to calculate some thermal correlators of whatever operator, starting from a theory defined on a Schwinger-Keldysh contour. This means that in your path integral that you consider, time doesn't go necessarily from doesn't go from initial time to a final time, but it does it forwards and then backwards. And this basically creates this form of the path integral in which for each field that you want to describe, you're going to have two copies, one for each time branch. And all of this is defined maybe on a thermal state if you're interested in thermal physics, otherwise in something else so if you're interested in disordered systems. But in general, you have this fundamental functional, generating functional. And the reason why you may care about this type of time contour as opposed to what we usually do, for instance, to calculate scattering amplitudes at zero temperature, is that, for instance, by doing a very simple change of variable, you have direct access to all the causal propagators, which are ultimately what you're interested in if you're interested in transport. So now, how these EFTs should emerge out of this picture is in the following way. So we just invoke the usual Wilsonian picture of a normalization flow. And what you can think is to divide your degrees of freedom into slow and fast, and to integrate out the latter. So what this, what this EFT approach advocated was actually that, unlike, as I showed here, unlike this action factorized between the fields of type 1 and type 2, after a normalization flow, you should land in something which in general couples the degrees of freedom. And well, this should be actually slow modes, not fast, but anyway, sorry. These are less than symbols. And in general, this will depend on the state upon which the theory is quantized, and we'll have this more complicated structure. And in these papers, Crossing collaborators worked out a few constraints that this effective action must have. In particular, if no other structure is present, you're going to have some constraints that do follow from unitarity. So what you see from these constraints is that in general, this effective action will be complex, should be complex. This is not forbidden from unitarity of the microscopic theory. And the field can be correlated, so fields of type 1 and type 2. And if you have symmetries, you're going to have extra constraints. If you know that there is a certain order parameter, you're going to add that as well. But in general, the rough idea is, given these constraints, I'm just going to write down systematically what are all the consistent terms that I can add in this action. Now, so what's interesting, though, is that the imaginary part of this effective action that I'm talking about does encode the dissipative effect. So, and just to give you like a very cheap way to see this is if you just have a look at this exponential here, this is going to become a decaying exponential. Hence, you have transition amplitude that decay, and they encode dissipation. Yay. So, however, like something that should be really stated precisely is that we don't really know much about the explicit nature of this flow that leads you from a UV QFT that is in general unitary to this open theory in the IR. And so we'd really want to know what's happening and what are the mechanisms that make all these terms come into existence. And this is the whole point of this talk. So what I'm really caring about today is to try to give you a window into what are the intermediate steps of this RG flow and why these terms should actually emerge. And yeah, this is it for the introduction. Are there any early questions so far? Okay.
Maybe just like a clarifying question, because like in the work of Cross et al., they like remain ignorant on what the modes are that they integrate out. And what you're saying is that you're going to precisely teach us what are these modes, or at least what are their nature that they're integrating out to get to the EFT.
Oh yeah. So okay, that's fair. So yes, so what I meant in this introduction is actually it's kind of just a schematics. So in general, if I gave you like a fundamental theory, the idea is you would know from the fundamental theory what you're integrating out. In their picture, though, in a way, what they're doing is they're guessing what's at the very end of the flow. So one of the reasons why I wanted to have a look into the calculations that I'm going to present is actually try to get a handle on how stuff can happen, like in between. Why would you land in something different? But yeah, this is a very initial study in that sense. I'm gonna admit. So thanks.
Yeah.
All right. So before we get to the actual part where I tell you what the new results are, let's have a step back. Just have a brief review of how a closed time path formalism in QFT works. So in general, so what I want to do is in some sense doing something that is like as general as concrete as possible, in a certain sense, I do not want to consider any particular special case. So for this work, I'm going to do the stupidest thing that I can do, which is I'm just going to consider a simple perturbative QFT that has no special feature. So no SUSY, no large degrees of freedom, doesn't have conformal invariance. It's just going to be our workhorse 5 to the 4 theory, a single boson theory. Um, what I'm going to be saying probably doesn't really depend shouldn't depend really on the theory in under exam, but this is like this is where you can distill the content. So this is what we picked. And so like in general, in a thermal QFT, what we're interested in is to calculate some thermal expectation values. So you can imagine you have a trace of a thermal state and a bunch of operators evaluated at some point in time. And in order to calculate this in a path integral formalism, what you really want to do is you want to quantize the theory on some, in general, complex time contour that connects the some initial time to the same initial time translated by negative I beta. And possibly, in case you do not want to do any analytic continuation, you would really want your contour to go through all the time points that you're interested in. For instance, if you're interested in real time or stuff like that. And at these endpoints, we will impose, at least for 5 to the 4 theory, periodic boundary conditions. Here I put an asterisk because the slight precisation has to be done. If I'm working with the fermionic theory, this is going to be anti-periodic conditions. If I do have conserved charges, I have to slightly modify this into what they're called quasi-periodic boundary conditions. We're not going to be concerned with that, fortunately. Anyway, like in practice, so what I mean by all of this is that all the functions that get into the path integral of the theory, their time argument will not be defined on a straight, let's say on real time, but will be defined on this complex time contour. And because this is a perturbative field theory, what I'm going to be doing is the thing that we always do, which is I'm going to see the functional integral as some interacting part acting on a free part, which I can calculate by completing a square in the path integral. Now, in a thermal QFT, there is a bit of a precision, there is a bit of a detail that has to be fixed about this, which is that in order to complete that square and calculate the integral and not break the periodic boundary conditions, you also have to assume KMS relations. And I feel this is something that was worth mentioning because when we think about KMS relations, we always think about relations between 2-point functions of a theory. You can actually prove that this symmetry of the boundary conditions of the path integral is in one-to-one correspondence with that statement. And I didn't know about this, so I found it cool. Anyway, another important relations in the following will be just the relation between the spectral density of the boson and its free propagator, defined on this whole complex contour. You see that there's like quite a remarkable difference here in the fact that in general, if I'm in a thermal field theory, not only I will have the theta, the time order things, I will also have a Bose-Einstein distribution factor that will get into the Feynman rules at some point. And yeah, so quite remarkably, you can actually prove that this relation between the propagator and the spectral density of the boson is still true even at the interacting level. And yep, it's a long demonstration. It's a long proof. I'm not going to do it here, but here's a reference if you want to have a look at it. Nice. So now, so far, I did not really specify what this contour gamma is. To make any concrete progress, you will really have to pick something. And you can have as many choices as you want. So here, let's review a few. So what you would do in your first course in thermal QFT is to take the straight vertical line that goes from Ti to T minus I beta. And that's what gives rise to the imaginary time formalism, which has simple Feynman rules with the kind of oddity of having discrete imaginary frequencies. But in general, if you're interested in real-time data, what you would really like to do is to include in your contour the whole real line. And the way to do this would be to insert some fold in this contour, which I represented here in the red contour. And technically, you can add as many folds as you want, which can be very useful if you're interested, if you're like a quantum chaos person and you want to calculate some autocs. And but we like literally anything that satisfies this simple relation um, is okay to quantize your theory. And this comes from, I think, convergence of the spectral representation of the propagator. So great. Uh, Go for it. Okay, so I see what you're saying. Uh, so I mean, here what I'm using is actually yes, no, okay, yes. In a sense, yes, because you have real time, so you really have dynamics here. Uh, so I would say that my understanding of how this thing works is that there is like a general belief that the choice of contours shouldn't really inform the physics you can extract out of the out of your choice. Because for instance, let's say the advantage of a real-time formalism is that it gives you, for instance, like direct access to, let's say, a retarded propagator. And in line of principle, you should be able to analytically continue an imaginary time propagator to get the retarded one. So my understanding is that there is a sort of an assumption that whatever you do in one formalism, you can recover in the other. Uh, it may not be straightforward because there are some non-uniqueness theorems on these analytic continuations. Uh, I'm not sure it does answer to your question. Uh, okay. Okay. Anyway, so once you land on your favorite choice of time contour, well, you can just plug it into the expression of the previous page, and you can calculate the Feynman rules of the theory. So, and from now on, I'm gonna pick gamma to be the single real-time fold. So this red contour up here. Now, what I think is worth pointing out is actually that as gamma is actually made by four intervals. So if we follow the logic that each time interval, so you would define a field on each time interval, well, you could expect to have four fields, and so that this matrix describing the propagator of this multiplet should be a rank matrix, a rank four matrix, and in general, that's the case. So how do we get to the doubling of the degrees of freedom? Now, there is this funny thing that the path integral, under some mild assumptions, does actually factorize into, apart for the horizontal lines in the time contour and the vertical lines. And for the following, it will be important to know what these conditions are. So let me review them. So you really want, uh, so the external sources to vanish at real time, at infinity in real time, which, well, fair enough. But there is another condition that you do have, which is you have to assume that throughout the calculations you do, the free spectral function has to be a function and not a distribution. So let's say in a free theory, the spectral density is usually a mass shell is proportional to a mass shell delta. So what you really want to do is to regularize it, let's say with a Lorentzian peak, and this is nothing different from the I epsilon prescription that you saw in all of your courses on QFT. However, if we talk about thermal physics, this also has a physical interpretation, which is if you have a particle that is spread out by a parameter eta, in this case, what you're assuming throughout the calculation is that particle is that that particle does have a finite lifetime of order 1 over eta that you then send to infinity at the end. So that means that when you do calculations, you are really considering that the particle is unstable with a very long lifetime, but unstable, and you take it to be stable at the very end of the calculation. Like this is going to be useful in the following. So, and if you are fine with these assumptions, then this factorization for the path integral happens. This is actually why then when we do thermal field theory, we usually have this doubling of the degrees of freedom, because you can integrate out the fields that live on the vertical lines. You don't care about them anymore if you're interested in real-time data. And well, that's how it actually works. Cool. I promise you, these are not just this is not just me rambling. This is going to be useful in the following. And anyways, just to conclude this section, so once you make all these choices and all these assumptions, you get to the Feynman rules of the theory that we're going to use to perform the renormalization of the theory. And they have this I think there are like a couple of interesting features about them. So when you consider like the propagators of the theory, the propagator is a 2x2 matrix that has off-diagonal terms. And it's quite interesting to see that in on the single real-time fold, actually. So you have that, let's say, the single type internal line, so let's say the line that goes 1 to 1, 2 to 2, has a kinetic term plus a thermal contribution that is entirely localized on a mass shell, whereas like the off-diagonal part just has this mass shell term. And this is quite interesting that all of the thermal contributions live on this localized thing, because actually this is how you would prove that working with the thermal field theory doesn't impose you to add extra counter terms to counter new UV divergences. That's actually how you prove it. And the second thing, which is very interesting, is that if you go through all of this derivation, because of the form of the functional integral of the generating functional, the vertices are actually correlating just fields of the same type. And this means that these are local interactions. Okay, so this is a good moment to stop. If you have any questions, I'm going to drink some water. Otherwise, I'm going to keep going. Oh, so I see. So I think what I want to answer probably is that it doesn't really have much of a physical meaning, except that if you want to calculate the square of a commutator of two operators evaluated at different point in time, you may need to do something like that to ensure the time ordering, the correct time ordering of what goes in the thermal expectation value. So yeah, so there is like this work by Douglas Stanford on chaos in weakly interacting systems, where actually he does it explicitly for a theory that is somewhat similar to the one that I'm working with.
Yeah, for example, you will have different kind of faults if you have a time order correlator and the out of time order correlator. You will place them at different points, your operators on the doubled folded thing.
Yes, exactly. So the point is that you can kind of take this raw talk and make it into a contour ordered thing because you're still, going back and forth. So, okay, good. So, okay, we finally got to the interesting part of the talk. Thanks for bearing with me so far, which is let us now try to actually see how these features that I mentioned before actually are generated by an RG flow. So to start with, not just because I'm lazy, I'm going to assume that this theory I'm working with has a hard UV cutoff. This has much to do with the fact that being interested in transport, what I'm really thinking at is field theories that emerge out of some underlying lattice structure. So in a sense, these are field theories that have a natural UV cutoff, which is the lattice length. of the underlying structure. It's also very convenient for calculations, but the results do not depend on this really. So what I'm going to be doing is the usual thing that we do when we perform a Wilsonian procedure. So I'm going to consider slow modes and fast modes defined, let's say, in a shell between a lower cutoff and the original cutoff. And then by using the fact that the quadratic, so the free part of the action, factorizes into slow and fast modes, you can just take the free part of the fast modes and use it to define a Gaussian ensemble, so that you can take averages that you know how to take because they have a diagrammatic expansion in terms of Feynman diagrams. And what you can do, if you do have, if the interaction is small enough, let's say G is suitably small in the Lagrangian, then this can be expanded perturbatively, and the first few orders are here. And so I would say like one interesting bit of this expression is actually when you take these averages, when you take this diagrammatic expansion, so you're going to have that, you're going to have field, all the internal lines and external lines will be of type 1 or 2. But interestingly, external lines are slow modes, internal lines are fast modes. So that's what you mean by integrating out on the fast modes. Okay, cool. So now I just have to calculate some Feynman loop diagrams. We all studied how to do that a long time ago in undergrad. Before doing that, let me just specify what I do mean by cutting off the theory, because in general, what we do when we have a hard, let's say a hard cutoff in a Lorentz invariant theory, some relativistic field theory, what you're going to do is you're going to go to you're going to do a weak rotation, go to Euclidean time, and carve out a Euclidean ball of modes, and you're going to use that as your, let's say, hard UV cutoff. But in general, so this is a Lorentz invariant prescription, and there is really no need for us to have a Lorentz invariant prescription because I quantize the theory on a state that does break Lorentz invariance. So I'm going to do something different this time. So what I'm going to be doing is I'm going to leave the integral on frequencies unbounded and put the cutoff on spatial momenta only, which again, if I'm really thinking at a lattice length, that's kind of the honest thing to do. It's also nice because it makes calculations much easier. Anyway, so first correction that I can calculate is going to be the linear term in this expansion. So let me just maybe come back for a second. So the first correction that I'm calculating is this linear part here. So the linear part, it does not mix fields of type 1 and type 2. So it just contains the two bare interactions, surprise, surprise, and it does contain a correction, a loop correction to the mass term. And this is going to be equal and opposite for fields of type 1 and type 2, so which means they have the same mass after a normalization. And well, this is the expression. If you're interested in it, it's not particularly illuminating. I think what's much more spicy is what happens in the following order, which is the correction to the coupling, which is actually where you get to the heart of this result that we have. So there are three allowed corrections to the 4-point function at the order I considered. And diagrammatically, these are this loop made of, let's say, only type 1 fields, this loop made of type 2 fields, and then you have this guy here, which is technically a correction to the operator phi1, phi2 all squared. So this is a candidate for the type of interactions we're after. We shouldn't really be stopping here. We have to calculate the loop and prove it's not zero before saying anything. So anyway, so let's try to calculate these loop integrals. And for concreteness, I'm going to focus on just the first one. So what you're going to do is, as before, so, well, I should say this, because I'm interested in corrections to these couplings, I'm thinking on the lines of I want to work close to the critical dimension of phi to the fourth, which is 4. And so I really do not care about the momentum dependence of these guys here. So on the dependence of the external momentum, because that would just add, uh, you know, would just add derivatives to these operators, thus giving you something that is irrelevant in the IR. So I just throw it away. I set the external momentum to 0. Anyway, you just substitute the expression for the propagators, and you get this horrible expression here. Not very illuminating, but you can improve it. So you can use some identities on the theory of tempered distributions, and eventually you get to this expression in which you do have that. So one part of the frequency integral is finite and has this expression, and then you have this thing here that is disgusting, and it contains the square of a delta function, which is ill-defined. We don't really know what it is. And the question is, well, first, how do we deal with that? But interestingly, you can do the calculation for the other two loop corrections that I showed you in the previous page, and you keep getting this structure here. And apparently, this is coherent with a theorem that exists that has been proven in the 80s about the fact that terms, so in a perturbative expansions of 2-point functions, all these terms that contain like delta squared and all this kind of crap, they have to cancel each other. And a corollary of that theorem is that this cannot happen for 4-point functions, which is kind of depressing. So we need to learn how to deal with these. And so we need to understand a bit better actually what the structure that is making this divergence appear. And this is a known structure in thermal QFT. This is called a pinching pole singularity. Not sure how much you're familiar with it. It's kind of a niche topic. But anyway, strictly speaking, this is something that happens whenever you have two second order poles that in a certain limit, in this case, eta going to 0, just pinch an integration contour on the complex plane. This is something that was known to people doing S-matrix bootstrap in the 60s, and then it disappeared from the literature for 30 years and reappeared when around the time where this guy started working on thermal topics. So anyway, what's also very important, I think, to recognize about this type of singularity is that it's really a product of an it's an artifact in the sense that it's a product of an assumption that I made at the very beginning of this calculation. And let's see actually how you can solve it. Up to this point, are we happy with everything? Any questions? Okay, fantastic. Great. So the way in which you can kind of resolve this type of singularity is I gave it this stupid name of spectral widening, but really it's something that happens as soon as you put your phenomenologist hat on. You're going to remember, as I said before, that in a perturbative thermal QFT, like the fundamental degrees of freedom are not stable particles because interactions give a finite lifetime to virtual particles. So if you have a look at what the spectral function looks like in a theory like that, for weak coupling, you can expand it and you get this expression here, which really looks like the regularized delta function we had before. So, and the spectral width here is something that, so you can prove that is for phi to the 4 theory is order g squared in the interaction. But importantly, it's really just proportional to the imaginary part of the self-energy of the boson. It's quite interesting, like this quantity is known to be 0 for zero temperature theories. However, in a thermal theory, is no 0. So you have to deal with this. So like the very brutal way we had to deal with this singularity then was to just assume that we shouldn't trust this prescription that has been used so far of taking eta to 0. That's fine for 2-point function calculations because you don't care about what you do to the singularities because they cancel each other. You should really take this eta in a way to match the two spectral densities. And the minimal way in which you can do that is you have this 2 eta 2ek, which is, well, it's a dimensional factor that you can calculate. It can explain you later if you want to, but it's really boring. Then you add this g squared here and some phenomenological constant kappa. At this point is just a phenomenological constant. This is very nice because it makes all of the divergent expressions that we see so far, converge. It makes them finite. However, the cost you pay is that you break down the perturbative expansion. And let me be more concrete about this. So what happens is that if I take the expression that I had before, I solve this integral explicitly for a finite, but so let's say in a small eta expansion, and then make this substitution, you're going to see that this integral that I found here is now proportional to 1 over g squared. So you have to be careful here, and you have to go through the careful steps of understanding whether this means that we have to add some other loops to our calculation. Because, strictly speaking, let me make maybe a brief parenthesis here. But what this statement is telling you is that whenever in a loop integral you have two internal lines that carry the same momentum, they get a factor of 1 over g squared, which means that, loop integration, so higher loop integrals can actually contribute at leading order. So whatever will follow next can be trusted only if the momentum shell we integrate out is thin enough. I'm going to make this point later as well. But anyway, so if we can check that the expressions up to the perturbative order that we used actually are not affected by this substitution, this is fantastic. So what we end up with is this effective field theory, which is quite nice. It kind of looks like the one, it kind of looks like the theory we started with, but there are like two notable differences. Well, first, maybe the most clear is that now we generated, so pinching pole singularities actually do generate this phi1, phi2 squared term. It's quite nice. And the other term, the other thing that happens is that if you have a look at the coupling in front of the self-interactions of the two bosons, now rather than have there being the same coupling, they're the complex conjugates of one another, which is, it's something. So anyway, what you can do, by the way, just so that we see them at least once in this talk, I should say I tried to make this talk more about the ideas behind it and less about the horrible expressions that come out of the calculations. If you have questions, please ask. If you want me to be more technical, I can talk as much as you want. But anyway, so the couplings have these following expressions that, as I said, they're valid if the momentum shell is thin enough. What I mean is the following, is that the substitution that I made before, as I said, enhances higher loop diagrams. So you have to be careful that higher loop diagrams do not contribute at this perturbative order. However, I have still this integral on the spatial momenta, and for higher loop diagrams, these are going to be more and more suppressed the thinner I take this let's say this shell that I'm integrating out with. Very importantly, to conclude this section, you can take these expressions and ask yourself, is this effective field theory with this weird regularization that I used, does this actually obey all the unitarity rules that it should? And the answer is yes. So this is actually how, in a certain sense, this is how you should think as the procedure that gives rise to these effective field theories that Crossley and collaborators they talk about. And before I continue, this was a lot to take. So are we okay with what I said so far?
I had maybe a question. So
Yeah, go for it.
that's quite nice. So somehow, like in this theory, you get the action that Crossley et al. Like formally write down that these are effective when integrated on modes. The thing that they have is that in this effective theory, they have kind of a modified KMS condition, which they call this dynamical KMS condition.
Oh, yes.
So can you verify directly on your effective action? I always had trouble having intuition for this dynamical KMS. Like, do you have any?
Okay, so my understanding is I'm going to say the following. Uh,
Okay.
my procedure doesn't give any any indication on how you should think of that for the following reason.
Okay.
So my understanding of what they did for the KMS for this dynamical KMS condition is that it's really something that you get if you combine, KMS with some time inversion symmetry. And
Mm-hmm.
so what I did doesn't require any of that. So doesn't really give an input. So,
Okay. So it did.
I could start with a theory that is not time reversal invariant. I just go through the exact same procedure.
Yeah.
It would be interesting. This is one of the things that I completely forgot to put in the conclusion in the last slide. So to
Yeah.
actually take a theory that doesn't have this sort of extra symmetry, so it doesn't
Mm-hmm.
have time reversal symmetry, and see what happens. Do you get something that violates these unitarity bounds? I don't know. I gotta admit, I would say at the very origin of me dealing with this was that
Mm-hmm.
I couldn't really understand what this dynamical KMS symmetry was. So you
I
got me
agree
on
with
that.
you.
It's
I completely.
it's very very confusing.
Yeah.
Uh,
Okay. I'm happy I'm not the only one on that boat.
no, but we can chat about that later. It's not the first
Okay.
time I
Perfect.
hear
Thank you.
this.
Perfect. And
Okay,
thank you.
fantastic. Okay, so how am I doing on time? Oh yeah, fantastic. Uh,
Yeah, you have 15 minutes or even more.
oh, great. Okay, so let me then talk about these actually weird critical structures that emerge out of this picture, because I think this is where I think like most of my interests lie now within this larger framework, which is the following. So I have explicit expressions for the coupling, so I can get the beta functions for free. I just have to take a derivative. Moreover, what's interesting about this whole procedure that I make, it's true that it gives you reliable expression for the coupling in a thin shell limit, but that's enough for the for the beta functions. So I can have them, and by definition, let's now have a look. So let's now have a look at the fixed points of the renormalization flow of this effective theory. And I have a look at that, and well, I have to have all these equations having to be zero at the same time. I look for solutions, and I just find the Gaussian fixed point. And I want to stress actually that because now I'm in general, I can think at the type of theory that I have as an open EFT. This may actually be something that follows from the restriction that I made on the initial conditions of the flow, which is I impose that I'm starting from a unitary theory. So I'm not really fully exploring the the coupling space of the full EFT, of the open EFT. But anyway, more comments on this later. So another interesting thing that I could do is because I find this result boring, I may ask myself, well, what if I restrict to a smaller class of observables? So, for instance, I could think at correlators, the diagrammatic expression of which does not include, let's say, G cross and G bar. So, if I think at that type of correlators, like I don't know, there are like a lot of three-level correlators of this EFT would be of this kind. Uh, this correlator, if you write down its Kalan-Szymanczyk equation, will see a fixed point, and I'm going to say fixed point, uh, if I just require there's a weaker condition here. So if I set to zero some of the beta functions. So let's try to do this and see what comes out of it. That was our idea. So these are the equations that you have to solve. And the only point that I want to make from these expressions is that they are horrible. So you cannot solve them analytically. But you can either solve them numerically or you can do some low temperature expansion and see what comes out of this thing. So we did. And we solved this numerically for, let's say, at the critical dimensions and slightly below, and for temperatures that are finite, but let's say below the cutoff that I picked. So, and you get something that looks like this. By the way, just notice these conditions that I have from the beat. So the couplings. So especially the coupling G became complex. So you have that this equation will have a solution in the complex plane, which means that now I will look for like this sort of fixed points, not in R2, but in C2, and see what comes out of it. And you get something of this type. So now the curves, so the arrows of the curves point towards lowering temperatures. So what you see is that for each number of dimension and temperature that you consider, you find two fixed points. And at the critical dimension, you see that they collapse. So it's going to be the line where both the blue dashed branch and the red branch do collapse to the Gaussian fixed point. If you go slightly below, you're going to have a Wilson-Fisher fixed point. That's what we all know. And so you see that this goes to some finite value of the mass squared that is real, some finite value of the coupling. You can actually check that the prediction matches what you know from Euclidean field theory in 4 minus epsilon dimensions. That's fine. There's nothing still fancy about this, maybe. However, what you can also do is that you can study the linearized flow in the vicinity of a fixed point. And the eigenvalues of the 2x2 matrix that you have there will tell you what are the scaling dimensions of the well-defined deformations away from this fixed point. And you can do this, and you get this thing here. What I want to draw your attention to, and what I absolutely have no idea how to interpret, is the following. So if I work in exactly the dimensions, so for 4 dimensions, at finite temperature, so as I said, you have these 2 branches before in which they both go to the Gaussian fixed point. But if you have a look at the scaling dimensions that you calculate out of these linearized problems, you're always going to have that one of the two deformations is actually relevant because it has a go for it. Oh, sorry, it's just imaginary numbers. So this is just how do you say? Let me go back here. So this is just let's say the couplings that I made dimensionless with an appropriate power of the cutoff. Okay, that's what the tilde means. And so these are just complex numbers. So this is the real part and this is the imaginary part. And it's the same for the following, and it's the same in the following thing here. So these things here are the 2 eigenvalues of, so what you can do is you take the beta functions, like written down as a flow, you linearize them in the vicinity of the fixed points, and these are the 2 eigenvalues of the matrix that characterizes the linearized problem. Those 2 eigenvalues tell you, basically what they do is to tell you which, how would you say, well, the eigenvectors tell you which linear combination you should take to have something that is has a well-defined scaling dimensions, and the eigenvalues tell you with that scaling dimension. Yes, it's complex. I'm gonna get to that. I don't know what that means. So what's interesting though is that how would you say, you can still define in a certain sense whether one such deformation is relevant or irrelevant by looking at the real part of the eigenvalue. And if the real part is negative, it means that upon flowing, it goes back in, with some fluff given by the phase, by the imaginary part, but it goes back. So that's what you find, is that in exactly 4 dimensions, there is still something that you can consistently define as having one relevant and one irrelevant deformation. And maybe just let me show this stupid picture that we made for the paper. So we were puzzled, and then we kind of imagined this sort of funny experiment. So imagine like this completely fake and unphysical process, which is you start with your theory in exactly 4 dimensions, and then what you do is you heat it up. So, and which means that these 2 fixed points get away from the Gaussian fixed point. Then you stop at a given temperature. You lower continuously the dimension, and then you cool the theory back. So they draw these kind of nice pictures. So what you see, in a certain sense, is that this fixed point that has this, in a very, very broad sense, behaves like a Wilson-Fisher fixed point, even if it's exactly 4 dimensions, is continuously connected to what is actually a Wilson-Fisher fixed point by this process. So that's very puzzling. We have no idea yet really in how to interpret this kind of structure, but it's there. So here it is in all of its splendor. And I don't know, maybe I'm going to take questions after the conclusion reading slides because I'm here. And so just as a brief recap, what we did in this work was just found a consistent renormalization procedure that finally gives rise to all these nice terms that were assumed to exist in previous works in the literature. And we also started studying this critical structure that, as you heard me saying, we don't really understand quite well yet, of these open EFTs. So, and there's plenty of questions that are open, which is why I'm actually excited about this work. There's so much to do. So the first thing is actually trying to understand what happens to, let's say, the next perturbative order, or if I include, rather than using this phenomenological constant, which there's much to be said, but I could use, let's say, the full expression for the thermal width that I can calculate. Is just extremely difficult, extremely long, so we haven't done that. So what happens if we are more precise? On the EFT aspect, in my opinion, what's more interesting is asking what happens for like a non-perturbative theory, because as you saw before, the way in which I generated this imaginary part of the action and this cross couplings is very perturbative in nature. So pinching pole singularities are very much something that comes out of perturbative field theories. And it's not clear to me how this should be modified for a non-perturbative theory. So this could be done either with large N theories or, 5 to the 4th is simple enough that you can still apply an exact normalization group, probably. Maybe. I'm working on that. Is more complicated than I hoped. Anyway, the next question is, of course, what the hell are these new fixed points? Can we even talk to them as they are really fixed points? What's their experimental signature? So that's something I mentioned before. If you calculate the scaling dimensions at these fixed points, you get complex numbers, which if you follow through, means that in general you would expect the critical exponents at those fixed points to be complex. And there's a bunch of literature on that. Quite surprisingly, people have been thinking about it. They're related to usually unstable phases of matter, and anything that really has a hierarchical structure. So there may be something there that is of value, but another question that, again, probably I'm most interested in is actually trying to investigate what the critical properties of the full effective field theory, the full open effective field theory should be. So, because in general, there has been like recently a few studies about theories that are not unitary. Non-unitarity breaks C theorems. So what happens is that you can have some sort of exotic RG flows. And so like there's in this series of papers, it was conjectured at some point maybe we're going to get a chaotic RG flow. And my opinion, it would be very cool to tie the chaos you have in thermal field theories with that. I don't know if it's possible. That's a dream of mine. So anyway, that's me having rambled enough. So thank you for listening.